Hello friends, in this session we are going to understand a very important concept of electric flux. Now friends, while learning electric field lines and its properties, there was one property that we have understood, that if in the region which the electric field lines are more congregated, the magnitude of electric field in that particular region is greater, right? So the region in which if the electric field lines are more, if there are more electric field lines in a particular region, then in that particular region the magnitude of electric field is greater. Now on the basis of the same concept, we are going to understand electric flux. Now I am considering electric field lines. Now this electric field lines is passing through a surface whose area is A. Now electric flux is indicated by phi. Electric flux is given by the product of magnitude of electric field, which is and the area which is perpendicular to this electric field, So once again, electric flux is defined as the product of magnitude of electric field which is passing through a given area A, and this area is perpendicular to the electric field, right? Okay. Now we know electric field is a vector quantity, right? Electric field is a vector quantity, whereas area A, is it a vector quantity or is it a scalar quantity? We have always learned that area is a scalar quantity. So if area is a scalar quantity, then this particular electric flux has to be what? A vector quantity, right? However, electric flux is not a vector quantity, it is a scalar quantity. Here is the point where we define area vector. Now what is area vector? Area vector is a vector which is perpendicular to a given area. So this is the given area. A vector which is perpendicular to the given area is called as area vector. What is the direction of this area vector? The direction of area vector is always outside the enclosed surface, right? So we have an enclosed surface, and that enclosed surface will have some surface area, and the area vector will always be outside that enclosed surface. Now we will understand how to consider the direction of area vector using an example. Okay, before this we will come back to electric flux and then talk more about electric flux. So electric flux, so this has to be what? Area E. Electric field is a vector quantity. Area is again a vector quantity. So flux is equal to dot product of electric field and the area vector, and this is how flux is nothing but a scalar quantity. So in case if the electric flux is not perpendicular to the area vector, what will happen? Let's say for example, this is the surface and the electric field is in this direction, right? Okay. What is the direction of area vector? It is always perpendicular to the given area. So this is nothing but the surface. So it is always perpendicular to the given area. So this is nothing but what? Area vector. So what is the angle between area vector and E vector? It is nothing but what? Theta. So in this particular case, flux is given by phi is equal to E vector dot A vector. So flux is given by phi is equal to E into A cos theta, where theta is nothing but the angle between E vector and A vector. Whereas in this case, it can simply be given by as phi is equal to E into A cos theta. What is the angle between A and E? In this particular case, the angle is 0. So I can simply write the electric flux is equal to E into A. Right? Okay. So this particular equation can be written as E is equal to phi by A. Right? So that means if the region in which the electric flux is more, right, the electric field is more. If the area is less, however, in that particular area, in a given very small area, if the number of field lines is more, then flux is more, and because of which the magnitude of electric field is also more, right? So if we have a smaller area, and in that smaller area, if the electric field lines are greater, then the magnitude of electric field in that particular region, in that particular area is greater, right? So we know now what is electric flux. It is the magnitude of electric field which is passing through the area A. Magnitude of electric field, it is simply nothing but what? The product of magnitude of electric field and the area in which, through which this electric field is passing perpendicular. So what is the unit of flux? The unit of flux is given by electric field. So electric field is given by Newton per coulomb and area is given by meter square. So flux can be given by Newton per coulomb into meter square. So this is nothing but what? The unit of flux. Okay, now in order to understand this flux better, we will take one example. What are the examples here? We have a cylinder. The radius of the cylinder is R, and the electric field, uniform electric field, is along the axis of this cylinder, which is in this direction. Now the question is, find out the flux through this cylinder. The question is, find out the flux through this cylinder. Okay. Now, in order to find out flux through this cylinder, we will divide this cylinder into three parts. One is the left hand side plane, the plane which is located on the left hand side, and the plane of the cylinder which is located on the right hand side. And the middle portion, the circular part of the cylinder, will be considered to be the third region. Okay? Okay. Now, what I am doing is, I am considering a very small element of area over here, a very small element of area over here. So this is a very small element of area over here, right? Now, as I told you, how to consider the direction of area vector. This is a very small area dA which I have considered over here. Now this dA, since it is a area vector, now what would be the direction of area vector? The direction of area vector is always taken as perpendicular to the given surface area and outside the closed surface. So what should be the direction? It should be perpendicular to the given area. So this is the area vector which is perpendicular to the given area and outside the closed surface. So it has to be what? In this direction. So this is nothing but what? dA vector. Right? Now the flux along this region for first region is given by d phi is equal to E vector dot dA vector. Right? Now if I want to find the total flux, I require to integrate this throughout this surface. Right? So how do I do this? I can write phi is equal to integration of d phi. So phi for the first region is equal to integration of what is d phi? D phi is E magnitude of E into magnitude of dA into cos theta. Now what is the angle between A and E vector? Now see here, E vector is in this direction whereas dA is in opposite direction. So what is the angle? 180 degree. Right? Cos 180 is what? -1. So I can write phi for the first region is equal to E, okay, since electric field is uniform, integration of dA and minus sign. Why? Because cos 180 is nothing but what? -1. Okay, integration of dA. When I integrate this, what will I get? I'll get the entire circular part of the cylinder, the entire plane circular part of the cylinder. That means nothing but what? Area of a circle, which is nothing but what? Pi r square. Right? So phi is equal to minus E pi r square. Now let us find the flux which is passing through the middle portion of the cylinder. Right? So this was nothing but what? The flux for the first region. Okay. Now the flux for the middle region. I'll name this as phi 1 for convenience. Phi 1. Okay. Now for middle portion, I'll consider this small element of area. Now for this particular area, small element, what would be the direction of area vector? This is nothing but what? dA. What is dA vector? It is perpendicular to the given surface and outside the enclosed surface area. So that means this is nothing but what? The direction of dA vector. Right? Whereas, what is the direction of electric field? The direction of electric field is this electric field. See, this is the direction of electric field. In this particular case, this was the direction of electric field. So again, if I want to find the total flux for this given area is what? Phi 2. This is case 2. D phi 2 is equal to E vector dot dA vector. So phi 2 is equal to integration of d phi 2. I have to integrate such all such small flux which is associated with that area over the entire surface. So phi 2 is equal to d phi 2 is given by integration of d phi 2 is what? Okay, magnitude of E into magnitude of dA into cos, what is the angle between them? 90 degree. Cos 90. So if it is cos 90, what is phi 2? Phi 2 is equal to 0. So phi 2 is equal to 0. Right? Okay. Now, let us take this third part. Here, I will consider dA. Okay. What is the direction of dA? It is perpendicular to the given surface and outside the enclosed surface. So this is if this is dA area, small element dA, so this is nothing but what? dA vector. And what is the direction of electric field? This is the direction of electric field. Okay, so phi 3, this is what for third region, phi 3 is equal to integration of d phi 2. And what is d phi 2? It is what? Magnitude of electric field into magnitude of dA into cos theta. Now what is theta? Theta over here is equal to 0 because they are in the same direction. Cos 0. Cos 0 is what? 1. Okay. So phi 3 is given by E integration of dA. Now when I integrate this dA over the entire surface, what will I get? The area of the surface. So I can say phi 3 is equal to E into pi r square, right? So phi 3 is equal to pi E or pi r square into E. Okay. Now let us find out the entire electric flux. So flux is given by flux through this region, flux plus flux through this region plus flux through this region. So I can write the total flux is equal to phi 1 plus phi 2 plus phi 3. So what is phi 1? It is equal to minus E pi r square. What is phi 2? It is equal to 0. What is phi 3? It is equal to plus E r square, right? So plus E r plus E pi r square. So this will get cancelled away and the total flux comes to 0. Right? So this is how we can estimate, we can calculate we can determine the direction of the area vector. In addition to that, this example has reached to a very important conclusion. What is that important conclusion? That if any enclosed surface is kept under uniform electric field, the flux inside this enclosed surface is equal to 0, right? And this is true for all the enclosed surfaces which is of any shape. That means if this particular cylinder is not a cylinder, let's say for example, if we are replacing this cylinder with a sphere, even inside the sphere, the flux, the total flux will be equal to 0, right? So this is how you can use the concept of electric flux to find out the electric flux inside any particular closed surface, or you can also find out electric field inside the closed surface, right? I hope you have understood the session. Thanks a lot.